Good afternoon, everyone. Welcome to our panel on the loop optimization working group. So my name is Barton. I'm going to be moderating the panel today. I just wanted to give you a little bit of background. We started the loop op working group, I guess it was back in May or June. We sent out emails to the dev list, and so we're meeting bi-weekly Wednesdays at 11 a.m. Eastern time. We meet for an hour. It's a cross-geo, cross-company, cross-participant call where we discuss various topics related to loops and loop optimizations. So the agendas vary. We've had different presentations from different people who are doing different types of work with loops and loop optimizations. We typically have some discussions in terms of where we would like things to be headed in terms of loops and loop infrastructure and loop optimizations in LLVM. And so we wanted to have a panel discussion. We've got some of the more active members of that bi-weekly meeting here, and I'm going to let them go through and introduce themselves. And then I just wanted to open up and to have some discussions here with people in the room to come and ask questions in terms of loops and loop optimizations and get the opinion from the panel members in terms of what they think about what's on your mind regarding loop optimizations in LLVM. So, go ahead.
Hi, my name is Sjoerd. I work for ARM. I must confess I'm not participating in the call. Well, I should, but there is a bit of a personal bandwidth problem, but I will join. But loop optimizations, yes, I accepted the invite. Thank you. Because, well, loop optimizations are, of course, really crucial for us. If you perhaps know, ARM has now 3 vector extensions. We just added another one for the microcontrollers, if you saw my talk earlier today. So they are absolutely crucial for us. Also, just the very traditional loop optimizations like loop unrolling is absolutely crucial for our microcontrollers. I'm also kind of representing my colleague David Green here, who added loop unroll and jam, worked on dependence analysis. We still have a wish list. We also added, well, as you know, maybe we work on hardware loops. We are interested in software, swing modulus shelling. And in a previous life, I worked on polyhedral optimizations and data dependence analysis. So, yes, I'm very interested in loop optimizations.
Hi, everyone. I'm Reames. This is my second panel in a row. We'll find out if I know more about loop optimization than I do interprocedural optimization. So I'm with Azul Systems. We have a JVM where we have a top-tier just-in-time compiler that's built with LLVM. Because of my source language, my main interest in loops on a day-to-day basis is getting rid of those annoying range checks. Because of that, I am very practically interested in techniques for normalizing loops or extending existing loop transform passes we have to handle multi-exit loop structures. That's what I've been working on, well, off and on for about 5 years now. Most recently, I've been looking at things around sort of SCEV, which is scalar evolution, which is how we analyze loop induction variables, and its ability to reason about exit counts, and using that knowledge to sort of better optimize away range checks in certain classes of idiomatic loops for us. I'll also say I'm the pragmatist on this panel. I'm the person here who, you know, everything I do goes into my shipping product the next week and it has to work. So because of that, I have a very particular bias with which I approach things that tends to be pretty conservative. And I'm sure that'll be one of the interplays that'll play out here as we talk is sort of between the it should work this way, but it doesn't. And we'll have that as sort of one of the elements in our debates.
Hi there, I'm Michael Kruse, working at Argonne National Lab. In contrast to Philip, it might be more the visionary, so which can be seen. Last year, I gave a talk about what I think is not that good about loop optimization, how it's currently working in LLVM, and what my long-term vision would be, which is like kind of different. But I came into loop optimizations from my PhD thesis, which is using Polly, so fully automatic loop optimization of loop nests Did work there on high performance computing. So for high performance computing, loops are very, very important, like the bread and butter of everything. At the moment, I'm working more towards using user-directed loop transformations. So the approach from Polly is try to find a heuristic which finds the best, the fastest loop nest, which can be, which unfortunately is not, it's a very, very hard problem, and it might be easier to just give the control to the user, and the user tells the compiler what loop optimizations to do, and the user can try different options, which allows for rapid optimization. I have a talk about this tomorrow in the late afternoon, so if you're interested, come join me.
Great, my turn, I suppose. So hi everyone, I'm Finkel. I also work at Argonne National Laboratory. I lead our compiler technology and programming languages team there. And I've been working on LLVM for the better part of a decade now. So I've done some work on loop optimizations in LLVM. I've worked on the loop reroller. I worked on the hardware loops implementation that the PowerPC backend uses. I've worked on vectorization and other miscellaneous things. So I am happy to lend my expertise to this endeavor.
All right, so does anybody have any questions or anything that they would like to start with?
So I heard about the talk about Fortran and F18 project and so on, and so we know that there is a lot of opportunity when you have a high language like Fortran where the aliasing is more well-defined to really stress the loop optimizer, and I see that loop optimization are going to become, in LLVM, are going to become more important as we start to have Fortran front-end that is fully integrated in the LLVM family. What's your opinion of, like, just in general, kind of like gut feeling about the evolution of loop optimization? How do you see it going? Do you see it like, do you see Fortran driving more of this effort than from the C++ side?
So I think so Fortran on the lower level, I think it's not that different. So than C, C++. So what you have is some more informations about, like, if you have accesses to multidimensional arrays, these are not by the language rules immediately lowered down, but you have some guarantees about aliasing, which gives you a lot, some more opportunities to which loop optimizations you take. But with some analysis, you may also find the same opportunities in C, C++ code, with admittedly somewhat harder, but I would not see it impossible. There's a trend for the Flang project. They are going to generate some NLIR dialect called FIR, sometimes pronounced fire, which allows them to preserve, for instance, these multidimensional array accesses, which is important to know what might override what other access there, which currently LLVM IR does not have. But I don't see a huge disadvantage for LLVM IR there, since you can add some like metadata or intrinsics that convey such information from the front end to the optimizers, which currently, unfortunately, are lost in the LLVM IR.
So one of the things I see that's pretty exciting about Fortran is it's going to force us to work through a number of some of the aliasing specification issues, particularly some of the restrict semantic stuff. Hal over here could probably say a lot more about that than I could, but
I will do so.
Okay, well, take it away.
But continue, and then I'll do that.
So that's one of the things I think is going to be really exciting about having a community of people who are really looking at Fortran performance and trying to drive it, is we're going to start seeing all of the different areas where the language features between Fortran and C++ differ. We'll start seeing some of those functionalities in LLVM strengthen. We've seen it a number of times now with different front ends. We've seen it with Swift. We've seen it with sort of the Java front end we have called Falcon. And we're going to see that again coming from the Fortran community, and that's really exciting. Go ahead and add your piece about the restrict semantics, and I'll come back and add something at the end about another language dialect we're starting to see, which is sort of interesting.
Okay, cool. Yeah, so first I'll say that, you know, we've been working on this for a very long time in terms of trying to improve LLVM's handling for restrict-like pointer semantics, which, you know, in other words, we're providing a way to annotate within LLVM the fact that particular memory accesses don't alias because they are accessing particular objects that we know don't alias. And this is something that we've needed for C restrict local, you know, for C restrict qualified pointers. We've been able to do some partial representation of this in LLVM for a long time, but for pointers where the qualifiers are on local variables, where the variables appear in structures and so on, we haven't had a good way of representing this. There's been work, and in fact a lot of recent work on this, and where there's a roundtable later in the meeting as well. So if you're interested in this, then look that up. And so I think the outcome of this is going to be that we're going to have some kind of extension to LLVM-IR consisting of some combination of additional metadata and intrinsics that can be used to represent these features. Now, the nice thing about this is there's a large amount of overlap between what we need for C restrict qualified pointers and variables in Fortran, and also variables that we see in other languages as well, where we know something about the aliasing because of underlying object semantics. And so I think that this is an area, as Philip was saying, where, you know, Fortran is going to push us and make sure that, you know, we can represent a wide variety of semantics in this space. And that will be good for C and you know, C++ eventually, and Fortran and the like. One of the related thing I want to say is there's a part of the issue about, you know, when we look at loop optimizations, you know, loop optimization can be composed in various ways. And that ordering is often quite important. So I'm sure Michael will touch on this in his talk, but you know, this also speaks to, you know, how we can have an infrastructure, how we can have a path manager, for example, that supports being able to perform transformations in orderings that are determined dynamically. And that's really going to be a key requirement that we're going to have in the loop optimization space. And I think you know, the desire to have more advanced loop transformations is going to push us there. And the one other thing I'll add is that, you know, while in principle there's not much, you know, there's not necessarily a difference between loop optimizations that we can do for, you know, C and C++ and those that we can do in Fortran, except as Michael was saying, that the Fortran language semantics give us more information and make it easier to do. I think there's also another aspect of this, which is there's an aspect to user expectation. So, you know, users have more of an expectation that compiler will do these kinds of things for Fortran code, and that will also push us in a helpful direction. Now back to you.
Okay, so I was going to use your question to spin off in a different direction, not driven directly by Fortran, but other new things we're seeing that are driving some interesting loop questions for us. Is we've been looking more and more at data analytics pipelines that are implemented in Java and have some really interesting structures to them. You know, there's all kinds of, basically classic examples. You know, you're doing a database, you've got two selects, you've got an opportunity to do a merge on the filter. That, when lowered to Java bytecode and then lowered to LLVM-IR, creates some very interesting loop structure problems. Because an idiomatic lowering for that is to have a copy of the data that's being selectively filled in before going on to the next loop. And you might have multiple loops in a row as you have different filters applied to the data before you get to whatever the aggregation operator might actually be. And that really points to some weaknesses in our current loop infrastructure in LLVM, where you have to have a high-level symbolic understanding of what this filter action is doing in terms of like a selective copy into a new array, because it combines both loop fusion but also various forms of escape analysis and like heap to stack conversion and things of that nature that I think push us in some very interesting ways that we currently don't do very well at all. And I think whenever we hit a new dialect or sort of a new language, we're always going to find those things that are idiomatic for that language that point out the deficiencies in the current infrastructure in really interesting ways.
What would you? Sorry. I think that it sounds like a bit like doing the optimizations at that level is too late. I've seen like they have optimization frameworks specialized for something like linear algebra. It's something called LIFT for stencils, for other purposes, which do this optimization on a higher level and just lower later than trying to optimize afterwards.
So my problem is I have 5 different frameworks that all try to do higher level optimizations and then screw it up in different ways. And then I have to reverse engineer what they were trying to do and do it for them.
I have maybe a related question to my fellow panel members here, because I think also Hal touched on that. What we want is that the different loop optimization to be more easily composable, evaluate different strategy, pick the best one. What do we think about Polly? That is I think one of the, that is one of the things that Polly could do, was I think one of the promises that you could more easily on a mathematical model do transformations and do a number of them, and then maybe later go back to IR. What is the status of Polly? There has been some discussions on the list, but that is already quite some time ago to, I don't know, get some of it into trunk mainline.
So as a developer of Polly, I can just say Polly is great.
But is it going to stay there forever? Is it done? Is it finished?
As you said, I have a long-term vision how things works. One of the issues is people have this. So I think there might be 2 issues. One is this. Polly tries to combine 2 levels of abstraction in a kind of awkward way. So there's a higher one and still tries to keep connected to the LLVM IR, which makes it hard to manage. So we are optimized, but on a high level, but still have the lower level concerns in mind. The other one is that there are sometimes issues about the method it uses for optimizing. So for dependency analysis and finding the best schedule, it uses integer linear programming, which has the reputation of being worst case exponential one time. And I think the essential algorithms used by Polly do not necessarily need integer linear programming, but can be implemented by simple heuristics. More simple heuristics. If you could still enable like the full power of a linear program solver, if you want to enable it, but I don't think it's necessary for the bulk of the things you want to optimize. So that's what I would think. Or at least I would like to move to in the future.
Yeah, I think, so I'm not a developer of Polly, so you could take what I say about Polly.
It's my boss.
Yeah, well, okay. Grain of salt, but, I think, okay, so I mean, it's kind of interesting because, we've had these debates for a long time about whether we should have an ILP solver inside of the compiler and what that means, and some people don't like ILP solvers because they have, worst case exponential complexity. Of course, I could point out that a lot of the algorithms we have in the compiler, if you don't cut them off, also have worst case exponential complexity, so oh well. And the other thing is that if you're doing dependence analysis, and you're doing dependence analysis across, multiple index expressions, multiple access expressions, which is the common case, right? Then if you use the simple heuristics, which tend to be pointwise, then that always has at least quadratic complexity. And so worst case exponential complexity might be better in practice than quadratic complexity in the common cases. So I think it's not such a simple question as to which is better. It's really a question of how you cut off the various algorithms. And so I would actually be very happy to see an ILP solver that was written to LLVM's coding styles and would fit with the rest of the infrastructure. And if we had such a thing, then we could decide how to use it or not in particular cases. Okay, so that's my opinion on that. But I think the other thing is that a lot of the trickiness with loop optimizations, of course, is in the cost modeling. It's not deciding what to do. It's deciding what to do and not necessarily then doing it. So, and one thing about polyhedral optimizations, obviously, is you have to decide exactly how you solve the underlying problem, right? So, there are various ways you can do like dimension at a time solving, or you can do single scheduling, and there are many choices. One of the potential issues with the algorithm that's currently in Poly is that since it does dimension at a time scheduling, it doesn't really model tiling until the end of the process, right? So, but in many cases, tiling is the most important optimization that you need to do for the loop nest. And so the fact that that's actually somewhat of an afterthought, at least structurally, if not conceptually, then that's a problem. So I think that we definitely want to have better loop optimizations, and I think we should learn from Poly and then integrate something really good into LLVM.
So that's kind of my idea. So we can have use both. You can use interlinear program solver for everything you solve, but if it maybe not only enable the tire optimization levels, and for something that is very common occurrence, we implement something that only works for this common occurrence there. So we have the choice to do both and are very flexible between them. Than just compared to just using Poly or just using traditional loop optimizations.
All right,
Sorry. Awesome. Did it answer your question?
Yeah. Well, maybe I have a follow-up one. Could there be, as you say, there are many complementary approaches here. Could there be, well, for the polyhedral analysis, we need a lot of compute power to get an answer. Is a more, well, okay. But could that a more explicit form, is that more desirable? So could MLIR with some dialects define dialect? Could that be one of the ways to simplify things, to make things explicit and help the loop optimization? So kind of achieve what Poly also wants to do, but starting from a different way and a more explicit one, rather than trying to deduce everything. Could that be?
So, in my opinion, on it doesn't make a difference whether you work on LLVM-IR or an NLIR. There's some more expressiveness you can have on MLIR. So you have, for instance, affine loop, so you don't need to analyze again whether they are affine. They're just affine by language definitions. But I think this is a problem relatively easily solved. You can see whether an expression is of the form C plus AX plus BY, and etc. That's not the hard problem, and it still depends.
I think I disagree, because we need scefs to analyze loop access, iteration counts. That is all stuff you get for free when things are explicit, when your affine descriptions of your loop is described already, when access patterns are already described. You don't.
So, but we have scef.
Yes, we have it.
And we're good at working at low-level representation.
That is true.
So why give up the generality of being able to do it from whatever the source language is and restrict the work to only benefit the source languages that are using, MLIL?
Also, I think in the MLIR roundtable, they were also discussing introducing scef as a kind of language for for MLIR. So there's still, you still have index expression depending on loop variables
Sure,
in
sure.
MLIR. There
Sure,
you
Yes.
still need to analyze it.
So one of the places I think we could actually take some really interesting lessons from MLIR and things like it is figuring out what the common dialects that people want to describe are. So for instance, there's a long history of programming languages with array language constructs. And I think one of the things that we could do in LLVM today is sort of a inferred analysis of that array language over loop structures. So for instance, common map idioms, if this is add 1 to every element of this array, if this is add these 2 arrays together into array C, like there are common languages for describing operations on arrays and vectors. We should be thinking and writing in those terms, I think. And one of the things that excites me about the MLIR stuff is we get to see what other sets of languages start being used to describe some of these higher level problems. And then we can look at, can we infer those same languages from the lower level representation? I think that's where the generality and power comes from, but the ease of experimentation definitely is on the side of MLIR and things like that.
Yeah, was kind of what I was thinking about before doing the optimization on a higher level. It's the difference whether you do some pointwise operation on a matrix, or do some matrix inversion, and you do another inversion. You can eliminate that, which is kind of impossible to do it after you allowed it to loops. So, but your argument was you have lots of framework not doing that, and you still have to fix it for them.
So it was, and that is true. But so like the matrix space is one I have to admit I'm personally a lot less familiar with, even though I know that's you guys' bread and butter. But like recognizing existing loop structures and saying, oh, that's a matrix inversion. I have 2 matrix inversions back to back. The second one, I can eliminate this entirely. That feels like a frameable problem. Inferring those structures over the lower level IR. And it has the advantage of working for IR from any source, even if it didn't quite look like an inversion before the optimizer got to it and simplified away the other pieces.
Yeah, so Polly does it in one case, detects whether something is a matrix multiplication and triggers on a special optimization for that. So think on the lower level from the LLVM part would be probably the equivalent loop idiom, which converts like pop count, detects pop count, replaces it by intrinsics. We're thinking about something like that.
So like loop idiom recognition is sort of maybe the building block in this direction, but it sort of composes today 2 parts. There's the idiom recognition, and there's the idiom transformation. And today, those 2 are coupled very tightly. And sort of, I think there's some interesting room when we can recognize an idiom, but there isn't a obviously better lowering for that on its own. So, like, take a simple example. I'm adding, 5 to every element in this massive, vector in memory. If the very next loop is subtracting 5 from that same vector, that memory has not escaped, that opens up an opportunity that today we completely miss. But that is an idiom we could recognize and form a higher level description of what a set of sort of sibling loops are doing that enable a whole class of optimizations we don't do today.
So, this way. But it's also true that certain type of idiom recognition is easier to do at a higher level. So if you had, for example, an array language, that kind of operation would be almost trivial to do at that level. But once you lower it to a loop and maybe some other intermediate code, it becomes harder. So isn't there, instead of, I can see with the introduction of MLIR and some of this dialect that people are going to want to solve the problem at that level because it's so much easier to do that than doing it after you generate LLVM IR.
Be careful. I'm not arguing they shouldn't solve it at that level. They should. Like if that's, the short-term thing they want to do that benefits that user community, absolutely.
But if we want to have commonality and not duplicate effort, another way to do this is, like you say, to learn and then extend the expressiveness of LLVM IR to add the information that are missing today, and that it would be useful to have in the IR itself so that we can do those things at a lower level and benefit every front end, or at least a subset of this optimization that every front end wants to exploit.
So 2 points. The first one is something you said sort of in passing that I want to actually address, which is duplicated effort isn't always a bad thing. That's how we learn. We try out different things, they succeed or fail on their merits, and then we look at sort of what succeeded and we all take that lessons. If we have different views as to how things should be done, it's in fact okay to try both of them and see which one works out, and draw lessons from each and let them influence the other. The other is your point about should we extend LLVM IR to add missing semantic information? Absolutely, we should definitely do that. Let's figure out what's missing first. At the moment, like the array language thing I'm describing, what I find interesting about it is I don't know of any missing information required to do that. I think we have all of the information in the current IR and the structures it has, and it's relatively easy to infer. It may very well be there are problem domains that don't have that property, but we should look and we should examine them.
So to me, it sounds like instead of talking about loop optimizations, we're just saying, wouldn't it be great if we had a higher level of abstraction earlier in the compiler flow, right? But then, and that's a fine thing to say, but does C and C++ allow you to go straight from the front end language into that higher level of abstraction?
Yeah, I think, so I'm not sure I'd agree with your characterization, but the answer to your second question is no.
Well, feel free to push back on.
Yeah. And I understand why I think you got that impression, but I think that there are a couple of key distinctions I would draw. So, but to your second point, the answer is firmly no. We've tried this in the past in many cases, but as a very practical matter, for the optimization of C and C++ code, and also often for the optimization of Fortran code and other such things, you must perform inlining first. Or at least you must be someplace where you can perform a fairly sophisticated amount of interprocedural analysis. So, and for C++ code specifically, this is absolutely essential. So, most of the HPC kind of C++ code, I shouldn't say most, but a significant portion of the C++ HPC code that we see relies on abstraction libraries to abstract away, raw arrays and such behind some kind of interface we want to use with overloaded operators and all this kind of stuff. And if you don't inline or look through those operators, even though they're simple, and perhaps because they're simple, you can do essentially nothing. And so that's really important. So I think that you definitely have to have some layer there before you operate on that. And then I think to the second point, I think we are saying that we want some kind of higher level representation. But I think the key question is, from where do you get it? And I think that in many cases we can build a higher level representation and then operate on that in the IR level optimization pipeline. I mean, we do this already. This is what skev is, for example, right? I mean, we say, oh, it would be really convenient if I had an actual algebraic expression here, so I could see that a plus b plus c was a plus b plus c, and so on, and you can worry about it, you can reason about induction variables and such. And we build that from the IR in the pipeline. We have some complex reasoning there. I mean, Polly does this as well, right? I mean, it takes in IR, it builds a higher level representation, and then transforms it, and then generates more IR. And I think what we're saying is that we want to sort of walk farther down this road, and for the purposes of performing other loop optimizations, we also want to build a representation that we can then manipulate But we can do that in a way that's part of the pipeline so that we don't introduce hard phase ordering problems with forcing particular optimizations to always occur before other particular optimizations and so on.
So my follow-on question to that would be, how does halide fit into this picture for you? Again, like if we're saying, okay, well, if I start with C and C++, then I'm going to have to recognize certain loop structures, raise it into this higher level of abstraction. I can optimize it at that level. I understand you're already doing that.
Yeah, so
you know, it seems like halide is an attempt at like saying, let's just make a front-end language where, you know, we can start at that high level.
yeah, I think that, you know, the thing is, if you can start at that level, then I think that's great. But the other thing I'll say is that the framework that that Michael mostly has been working on to encode ordered loop transformations in metadata in the LLVM so that we can operate at that level was in some sense inspired by halide and related projects that had this kind of separation between the kind of recipes for doing transformations from the sort of encoding of the algorithm itself. And so I think that you know, halide obviously is is a project that uses LLVM, and it's a good part of the ecosystem and serves as a good example. But it's also served as an inspiration for some of the work that we're doing at the optimizer level as well. Anyone else want to?
I'll add on a little bit. I realize there's one thing we've all been assuming, but none of us have actually said. The reason these high-level representations are so useful is they give us an idea of how to reason about cost modeling that otherwise isn't like practical. So like I'll pick on Git for a moment here with loop fusion. We can fuse adjacent loops, but how do we know when to fuse adjacent loops? Without some higher level knowledge of the semantics of those two loops, it's really hard to assess that profitability, and you could very easily end up with a pessimizer rather than an optimizer. One of the values of having the higher level semantic information is it gives you clear evidence of profitability. One of the things that's really powerful about halide and sort of Michael's work is it shifts that burden of figure out whether this is profitable out of compile time. It turns it into some like god-awful offline analysis problem to figure out what the right set of transforms to apply is that are profitable. And then you record that result in the source code. That sort of is all motivated by this sort of same root problem, which is figuring out whether basic loop transforms are profitable is really hard.
Just to mention, I think it's even hard if you are in a higher presentation. Not only because their stuff goes into evaluating whether something is profitable that you just don't know at compile time. Like, how is the average size of your loop you're iterating over? You just don't know at compile time. So you can go a step further, do something like profile-guided optimization, or do it even in a JIT that iteratively optimizes depending on running measurement numbers you've got. But even then, it stays a hard problem. So really, the goal is first step. Yeah, we can do. The user tells us what transformations they want to perform. The user can experiment, have some ideas about what could be faster, tested, or we could even do this automatically with a approach usually called auto-tuning, a program that just adds random transformations in the program and just keeps the one which runs fastest.
So I guess this is where I put on my pragmatist hat. We're never going to solve the general problem here. So part of making progress is identifying what are the things that are idiomatic in the languages we care about, and making sure that we can identify the obviously profitable cases and doing them. So that's why I like the array language idea. Sort of it gives a way to frame obvious profitability for things that have been showing up in workloads I'm interested in. It's one of the places where I think having mini front ends like Halide, like Fortran, like Java is great, because what is idiomatic and easy, and what are the simple cases, will differ from every one of those languages, which helps prevent over-specialization, which is one of the dangers of the pragmatic approach I'm suggesting. So having that tension between different people wanting to solve slightly different problems, but also having near-term deadlines to solve them soon, is really healthy.
Other questions?
So I just want to touch again on the example you made about loop fusion, where you need to have some kind of heuristic model to decide whether loop fusion is beneficial. For example, if used to loops and you happen to find reuse or opportunity for simplification, that's probably beneficial. But in other cases, you may fuse loop and then you won't be able to vectorize the operation in the loop because you have a loop carry dependency. So yeah, you can solve that problem by adding a model that specialize that for different consumer, if I give like priority to vectorization, I may not want to fuse. If I want to like reduce increase reuse, then I'll want to fuse. But the other way is also you need to have some kind of tool that can undo a bad decision. So, for example, you may want to fuse, and then later on you decide that wasn't the correct decision because you happen to have more information and more context in the loop, and you're going to go and want to undo those kind of things. So I guess I'm trying to find out what I'm trying to ask. So do you see like?
Well, I mean, let me just comment on what you said specifically. So, one of the things that we have to decide when we think about the setup of the optimization pipeline is, we have, some portion of the pipeline is dedicated to, that's what we call canonicalization, right, to a normalization phase. And in that normalization phase, we perform optimizations that try and simplify the IR, right? And these are optimizations that hopefully do not destroy information, but are optimizations that are generically make it easier for other optimizations to fire when that's appropriate. And then after we do all of that, then we have a phase that's more cost model driven, where we're performing optimizations for particular targets like vectorization or what have you. And we don't really strictly divide this for practical reasons because we can't. Inlining, for example, I mean, the whole normalization part of the pipeline sits inside of the inliner, which iterates, and that's great when it devirtualizes anyway. But the inliner is cost model driven, right? And so there is some target dependence there, and that's all true. But there is this higher level question about how you divide things and what you want your normalized form to be. And so, one way of arranging this, which I think is desirable in this particular case, is to say that you can do simple loop fusion aggressively early in the pipeline as part of a normalization phase. This enables scalar optimizations in the combined loop body, and you can do this sort of if and only if you have a sufficiently robust loop distribution or loop splitting path afterwards to split the things apart when need be. And I think that's a desirable configuration for an optimization pipeline if we can do that well. And so I agree with you. I mean, I think that's one potential and I think a desirable way of setting it up. But it does require that you have this kind of inversion capability later.
Along the same way, inlining, you need an outliner to undo possibilities.
Yep. Yeah, inlining, outlining for the same kind of. Yeah, so this is also an interesting question about how much work you do speculatively, right? So someone earlier mentioned these kinds of planning phases as well. I mean, we talked about this for vectorization, right? Where we have, if you have a loop nest, right? There are lots of different potential ways you might vectorize it. For example, right? There's inner loop vectorization, outer loop vectorization. There are many variants in there. You can choose between adding branches or doing predication, or there's lots of options. And so, and one way of doing this is you generate a bunch of plans, and you then cost out those plans, and then you pick that seems to be the best one. And of course, there's a trade-off there because there are probably an exponential number of plans, and you can't generate them all. And so you have some heuristic to choose which ones you generate. And in some cases, for some optimizations, it's possible you want to, perform transformations either fully or in part, or you do the planning phases for them, or what have you, and then undo that if it turns out not to be profitable. And we've certainly shied away from doing speculative transformations in the main LLVM optimization pipeline, but I think this is part of the trade-off space for.
Why is that? Why have we shied away from doing that?
I mean, mostly because it's expensive relative to other things. But,
Going back to my talk last year, I had a suggestion how to do it, like the method how to do a cheap copy of a loop nest, so you can have multiple speculative execution without copying every LLVM instruction in there every time. You just copy a part of the hierarchy and reuse subtrees, for instance. So this would enable you. You do then lots of different loop transformations. You prune in between because you can foresee something is not profitable. At the end, you have a selection one. You want a cost model over it and select the one which is fastest. So which would essentially solve the problem, like which transformation would we do? Do we first? Do we do something speculatively in there? If you just have a cost model in the end, which tells us which is the one which runs the fastest.
Let's see. So we've ended up spending a lot of time talking about cost modeling, which is reasonable because it's one of the really hard problems in loop optimization. We only have a couple minutes left in our slot.
Yeah.
One of the questions I was hoping to throw out to the panel was, the things we've talked about are mostly longer-term efforts. What are the near-term things that by next year, sort of, LLVM dev, you'd hope that we could have actually fixed and made meaningful progress on, that advance us towards, what you think is the right long-term direction?
So, in talking a short-term or long-term?
Short-term
Short-term, next year, I hope to have this mark-lang transform in there, where you can specify what transformations apply. For everything else, I'm the visionist.
Okay.
So yeah, I think that, I mean, exactly. So to do that, we'll need some infrastructure for doing dynamically scheduled loop transformations, perhaps, and other miscellaneous enhancements. I think on the vectorization side, by the way, I think hopefully in the next 12 months we'll make substantial progress on transitioning the vectorizer to use the vPlan infrastructure. And I think that will certainly be important. I think we'll have a number of other loop optimizations in the pipeline. So there, simple loop fusion should be there. Hopefully we can get the loop rolling maybe in there, and by default when we're optimizing for size. I think we'll have probably we should have a basic tiling pass. We should have some other kind of loop optimizations in there that we're currently missing, and hopefully over the next 12 months we'll be able to all kind of agree on a general path forward for what to do in the next 12 months, where I think we'll end up with we have a lot of exciting things to do, but so that's my hope for the next 12 months.
Okay. Well, I'll throw out my hope for the next 12 is to take some of those loop passes you just mentioned and make sure they're resilient to multi-exit loops. It's one of the pieces that we've been sort of working our way through Loop Optimizer a bit at a time, and I think by 12 months from now we should be done. That will be really nice because it'll make us much more resilient to slightly unusual loop structures where we miss the opportunity to eliminate some exit branch that could have been eliminated but wasn't, and we'll just make our performance much more resilient. Sjoerd, you have anything?
Yeah, I'm thinking. So, yeah, we do a lot of work actually on loop optimizations. just maybe a funny one. So my colleague contributed loop and roll and gem. We are using this downstream, but not upstream. It's not enabled by default, that's what I want to say. Which is interesting. And I think there's a few more. So it's all there, but we could actually do a lot more, actually. So there's all sorts of, well, maybe not low-hanging fruit, but if somebody wants to have a play with loop and roll and gem, or more of that, it's already there. We use it downstream, but not enabled by default. Yes, we look more at hardware loops. Maybe we are going to look at some loop scheduling. It's too much to do.
Okay.
Yeah.
Okay, yeah, I think with that we are out of time.
Yeah.
So as Hal mentioned, we do have a round table. Mike, do you remember when it is?
Oh, for loop
For
optimization.
the loop optimizations, yeah, there's a loop optimization round table.
There is.
Isn't it
Yes,
right
it's
after
following
this?
right now, yeah. Yeah.
Yeah. So if you're interested in continuing to talk about loop stuff, follow us as we walk over to the round table.
Yeah.
Yes. Okay,
And
thank you.
Thank you everybody for coming.
Thank you.
Thank you.